now that we know how to graph polar coordinates, let's do some calculus on some polar coordinates. And let's start with areas. And before we get to the actual formula, the calculus part, let's take a look at the area of a sector of a circle. When we talk about area of a sector, that's a formula in like geometry or some time when we learned it back in third grade. Where if you had a piece of a circle of the radius r and angle theta, then the area that's bounded by that piece of a circle is 1/2 r squared. That seems okay. If you want to let pi go all the way up to 2 pi, or you let theta go all the way to 2 pi, then you're looking at the whole circle, and the area of the whole circle is pi r squared. So you can just see how that's going to work out. So what we want to do with polar coordinate now, and polar coordinate graphing, is maybe if we take an example of a rose petal, or one of those things. By the way, some of the things that I asked you to explore on your own was the cosine 3 theta. Do you guys know how this looks like? It's a 3-petal flower, right? So it'll be drawn something like this. Let's see if I could draw it from 0 to 2 pi. It goes down, goes up. Yeah, something like that. So the issue here in terms of finding the area, I want to just focus on just this part, is that if we want, when does this thing hit 0 first, by the way? This cosine function has, what's the period of this cosine function? 3 theta. How many times is it going to hit the x-axis? How would you graph cosine of 3 theta? It'll start up top. It'll hit 6 times. Right? Does that look okay? And then, so I'm curious about what this angle is. By the way, you're going to have to learn about these intersecting angles and stuff, or when the graph is going to intersect the y-axis to. So you're going to have to do some trig. So when is this going to equal to 0 first? Theta is equal to what? Any ideas how to find that? We need to do some jumping jacks for a minute. Wake up a little bit. What? Yeah, if you set r equal to 0, that's how you would find it. So let's set r equal to 0, and then by let us set r equal to 0, I mean you set r equal to 0 and tell me what happens. Pi over what? Pi over 6 would probably be one of the first places that we would get equal to 0. Okay? So the issue here and why this sector isn't quite going to work is that we have a problem that if we take a little bit of a little cut of this thing isn't exactly a sector of a circle, right? This thing is not a perfectly drawn out sector of a circle because this little piece over here is not it didn't come from the circle in the first place. So it's a little bent. Our ideal situation would be if that was actually part of a circle, and then that would be nice and perfect, but this is not. This is a little bit off. So what do? We cut it up into really, really small pieces, and then we add them all up, and then as we add them all up, we take more and more pieces, smaller and smaller pieces, until we get an infinite number, until we get a Riemann sum that changes into an integral. All right, so what's involved in this sector? We have an angle, we have a radius, and then we have, well, that's all, right? Just an angle and a radius. So our angle here, let's say our angle here will represent our change in theta. And our radius here, well, depending on what theta is, your radius is really dependent on the function f of theta. So to find that area of that circle, if we're approximating it using sectors, we would then end up, the area of that little sector is going to be, what is it, 1/2 r squared theta. And with our approximation, it's going to be 1/2, and then r is f of theta squared. And then the angle between them now is going to be our change in theta and how theta is going to change. So this is how your area gets added up and eventually becomes an integral if we go from whatever to whatever. Okay? So that's not, by no means, that's not a formal proof of this formula, but essentially that's what happens. You have a sector, and then we take a look at the sector in the context of a polar coordinate function that's being drawn out. So those little sectors will become part of a Riemann sum that will eventually become an integral. All right, so let's do a quick example. Since we are dealing with this rose petal, let's take a look at, we can ask ourselves, find the area of everything, or find the area of one petal, or find the area of half a petal. And I think either of those would give us the answer to the rest. Yeah?
So the area formula, it looks a little bit like pi r squared. So is that where that came from, the idea behind it?
Sure.
Okay. So like, is the change in theta, is that essentially like replacing pi? Like, except because you're putting it up in smaller pieces? So you just
Well, it'll be 2 pi.
Right, 2 pi.
Yeah.
Okay.
Well, in light of that little comment, why don't we do a simpler example, and let's find the area of this polar coordinate function from 0 to 2 pi. What is that? What is this polar coordinate function? Circle, radius.
1.
Circle, radius 1. Is it a whole circle?
Yeah.
Going from 0 to 2 pi, so it's a whole circle. So the area had better be, what's the area of a circle? Pi r squared. So if we put it in that formula, a is equal to the integral, and your limits are from 0 to 2 pi. You got the 1/2 sitting outside. You got your area function, which is 1. d theta. And so this is just 1/2. And we integrate 1 with respect to theta. That's just theta from 0 to 2 pi. And that would just be pi. So r is equal to 1. Pi times 1 squared is pi. That's the area of the unit circle. Yeah? Well, the direction's always going to be going counterclockwise and starting it at the positive x-axis. All right? So this is essentially pi r squared. All right, let's take a look at the cosine, and let's take a look at the cosine of 3 theta and do that example now. And for some of these, they don't give you the limits. They say, oh, just one leaf or one petal of one of these things. And so if you're given a problem like this, what you need to do is you need to know how it looks like, and you'll have your graphing calculators. How many people don't have graphing calculators, by the way? Okay, if you don't have a graphing calculator and you take a quiz and then you need graphing calculator, I have graphing calculators that I can loan you in that cabinet, so just let me know. And I don't think we'll be using too much graphing calculation today, but maybe every class, if you guys want to use it, I'll have it available for you starting next week. So in any case, you have to know how this graph looks like. You have to know what your theta limits are, especially if they don't give it to you, so that you can, you can adjust your limits. And you have to know where these graphs are going to exist, especially when the graphs go negative, and that gets a little bit more tricky. So I'm going to redraw what I drew earlier, and just when theta is equal to 0 and theta is equal to pi over 6 is going to give us half of a petal, and so to get the full petal we just multiply it by 2. Well, once you know that, you just plug it into the formula, since we have the formula already, right? So the area is going to be, let's multiply it by 2, since we're only going to be considering half of the petal. And then the 1/2 of the petal is going to be this integral, which is a 1/2 integral from 0 to pi over 6 cosine 3 theta squared d theta. Okay? So as far as I'm concerned, I'm done, because then you just find this from Wolfram Alpha or your calculators or whatever. I suppose I should find it. So the 2 and the 1/2 go away. We got cosine 3 theta. You can put theta or something else. And we want to square that. What happened? pi over 12. All right. Any questions? All right. Let's just see if we can do another problem. Yes.
That actually solves just for the 1/2 of that, is that correct? Or not? Oh, no. Wait, that's-
Yeah, and then these things kind of worked out. And if I want the whole thing, I want all 3 petals, I just multiply this by 3. Should be good. All right, let's do another one. Have you guys taken a look at the homework questions for 10-4? No? All right. What? There's no 10-4?
There is, but it's listed under chapter 12 homework.
Really?
I was a little frazzled.
Maybe it's like under the lab.
I'm still frazzled.
Oh, why is it listed after that?
Because the due date's after it's listed by due date.
Oh, it's listed.
Oh, because your labs are,
Yeah.
for 12, yeah. I'm stating what you already know. What you're saying,
But it's
yeah.
cool that you caught up.
I don't want to be in the middle anymore. I
All right, let's do one of these guys. This is number 5. So for this one, this is going to require some drawing and trying to figure out angles and things like that. So let's see if we could put this together. We got r is equal to 17 sine theta, and then r is equal to 9 minus sine theta. Any ideas how any of these graphs might look like? How does the first one look like? Okay, so I highly encourage you to graph a whole bunch of polar coordinate graphs just for fun. Take out a computer and look for some nice graphing programs online so you can easily type it, or if you really want to punch it in your, if you're just, sitting waiting for the bus or sitting in the bathroom, take out your calculators and just punch in a bunch of trig stuff in your polar coordinates and see how the graphs look like. And the idea is that you want to get familiar with this so that you're comfortable enough seeing the first one. Oh, that looks like it's going to be a circle that's has radius. I don't know. So this thing is a circle that's been offset. It's not centered in the middle, and this thing is some sort of cardioid or limaçon or something like that. All right, so I have a graphing calculator program that I can punch this in. And knowing the graph is half the battle. The other half is trying to figure out what the limits are. So this is that circle over here that will have radius, I believe the radius is going to be half of 17. Or maybe, yeah, so it touches at 17, so the radius is half of 17. It's centered, whatever 17 over 2 is. And then the other function is r equals 9 minus sine theta. Well, not quite a cardioid or a limaçon, but it's not a circle either. So the question is, how or where are these two graphs going to intersect? Oops. So let's see. Let's get a drawing of this, and we'll come back to this program to figure out our limits. Suppose we should figure out the area, which area it is we're trying to look for, so that we know what we're talking about. Area of the region that lies inside of the first curve, so we want the overlap, right? So this is the first curve, inside of the first curve, and then it says outside of the second curve. So how should we do this? This is a second curve over here, and you want things that are outside of that. So it'll be this area that we're looking for. Does that make sense? It's like, you know, they give you a bunch of functions, and inside this and outside that, and then so this is what we want. Okay? So a couple of angles probably to look for would be this angle over here where these two things intersect. And in this angle, but the symmetry is probably going to allow us to probably just cut this off over here somewhere. So maybe if we just find half of it, we might be good. Okay so far? Aaron looks worried.
Them equal to each other, and then use those as your points for the interval.
Okay, so if we set them equal to each other, they're both are equal, so we could say 17 sine theta is equal to 9 minus sine theta, and then see where we can work, how we can work with this. If we solve for sine, yeah, so bring the signs together, this becomes plus 1, so that's 18. Sine theta is equal to 9, so sine theta is equal to 1/2, and that turned out nice. Theta is equal to pi over pi over 3.
Oh, wait, no. Sine, I got
Pi over 6.
Sine? What's that? Okay. My bad. It's sine, right? Pi over 6.
That's 5 or 6, because it's the height of 30 degrees, which is small.
So pi over 6 will start here, and then where do you think the second angle is going to be? I mean, we can find it over here, but if we cut it in half and just do it that way, pi over 2 will probably cut this in half. So those might work as good limits. So here's the other thing you could do with your calculator, is that if you have an idea of what these angles are, you can usually just trace them, and you have to hit trace. And for this case, for this particular graphing calculator program, I can trace it, and it'll give me some idea of what the angle is. In this case, the angle is 0.523, which is probably, is it pi over 6? And then up top here, it's 1.5, which is about pi over 2. And then just to be absolutely sure, you can adjust your window and get your t limits to, instead of graphing the whole thing, let's say I want to graph from pi over 6 to pi over 2. So if you adjust your t limits in your graphing calculator and graph it, then you see that that's really the piece that you want. And then if you had a program like this, you can make it look cool. and say it's inside 1. Well, that didn't work so well. Oh well. So we know that we're interested in this piece of the area. And then if we find that and double that, then we're going to get what we're looking for. Yeah?
But also, when you go back, since it's a positive 1/2, then wouldn't the sign give you 2 answers? So that it would be pi over 6 and 5 pi over 6?
Yeah, so if we go to 5 pi over 6,
So you, and just in case you didn't want to double it and just do the integral from pi over 6 to
Yeah.
pi over 6.
if we go to 5 pi over 6, this is what you would get. But usually we want to try to be a little bit more efficient and
Yeah, kind of.
just look for symmetry whenever we can. All right. So we know that we're going to integrate from 0 to 2 pi, and by that, I think we're essentially done, right? So the area is going to be equal to, we're going to be 2 times half of what we're looking for. So half of what we're looking for is going to be the formula where we get 1/2 times the integral from pi over 6 is your lower limit, pi over 2 is your upper limit. And then now the radial distances, have to be subtracted. So the outer radius is, which one is this? So that's 17 sine theta. And then the inner radius is this one, 9 minus sine theta squared. Okay? So that's it. So it's up to you whether you really want to work this out or not, or just punch it into a calculator or computer. If you punch it into a calculator, you're going to get a decimal approximation of what the answer is. And if this thing's looking for an actual value, which I think it is, yeah, so it has this thing on the side, so it probably means it wants an actual value, which means you probably want to use a Wolfram alpha type thing. So let's do that. We're integrating 17 sine theta squared minus 9 minus sine theta. And you have to be careful where you put the squared, right? From where to where? Pi over 2. And the 2 and the 1/2 outside cancel. So we got 45 root 3 plus 21 pi. Suppose we should check to make sure that's right. And let's see. What? Oh. Oops. Root 3 21 pi. Okay, good. Any questions about finding areas? No? We're all good? Okay. So again, being familiar with polar coordinates would be good. So just look at a whole bunch of polar coordinates, even if it's not in your homework. Just look at a whole bunch of polar coordinate functions, plug them in your calculators, just to get an idea of how they would look like. What happens if you put a negative sign? What happens if you multiply the outside by 3 or 4? What happens if you multiply the angle by 2 or 3? Just try a bunch of things out. Jessica?
How would you want us to solve something like that for a quiz or an exam? Probably we're not going to use that for math for that. So
For a quiz or an exam,
if we got into
yeah, for a quiz or exam, this is what I want. Okay, just being able to set it up. And there's enough pain and suffering in there where I wouldn't want you to have to do sine squared theta on an integral. I suppose I can give bonus points if you actually work out the integral by hand, but that's not necessary. All right, let's see. The next bit of calculus is the arc length. And I guess I should have, well, let's see if we could do some mini derivation things here. And we could just look at the formula as a formula, or we can see where it actually came from. Let's see if we can quickly remember where it came from, or where it could have come from. So we have a polar coordinate function that's usually represented by r is equal to something with a theta in it. And then we said yesterday that there's a relationship between polar coordinates and parametric equations, and the way to do that is to make it look like x and y. So r cosine theta. So r is f of theta. So f of theta cosine theta, and f of theta sine theta. All right. Now we also knew the formula for the arc length if we have parametric equations. So arc length for parametric equations is, if you remember, was given by L is equal to, oh, now they use S. Some integral from parameters alpha and beta, and then the square root of x prime of t squared plus y prime of t squared dt. So the link between that formula and this new formula that we're coming up with is really, this is your x and y. Well, just take the derivatives and square it, and you should get that. Okay? So can I just trust that you'll do that and get the solution? No. I could do it, but I'd be the only one having fun. You guys would watch. That's no fun. So you guys figure it out. So take the derivatives, square it, and when you square it, you'll have sine squared and cosine squared's combination somewhere, and then you can just put them together, and then they would poof become one, and then you'll end up with a f prime squared and f squared. All right, so this is the arc length formula. Let's find out the arc length of a petal for our function. Oh, I suppose we should do the other one first, right? Arc length of a circle. Our first example. So let's do as our first example, what's the arc length of, what's the circumference of a circle of radius 1? 2 pi. So when we do this, we should get 2 pi, right? All right, so this is a circle, radius 1, from 0 to 2 pi. So according to this arc length formula, we need f. This is f. What's f prime? That's a constant, so the derivative is going to be equal to 0. We're integrating this from 0 to 2 pi, and we have the square root of 0 plus 1. And then that's just 1. So that's just 2 pi, which is what we expected. Circumference of the circle is 2 pi. All right, let's do one of those 3-leaf rose petals things. Example, arc length of, one petal r is equal to cosine 3 theta. So we know the drawing. If we just take half of the petal, then we just double it, and then that's the other half down here. So we'll just worry about going from theta 0 and theta, what was this, pi over 6? And that gives you the petal. So what do we need? We need f. F of theta is cosine 3 theta. F prime of theta is negative sine 3 theta times 3. And so we need to put that into the integral under a square root and each of them squared. So the arc length is going to equal to the integral from 0 to pi over 6 and the square root of f prime minus 3 sine 3 theta squared, and then f cosine 3 theta squared and d theta. Okay? And you're done. Unless you want to find the answer and then you plug it into the computer, yeah?
So that S is just half of it now, or is that?
Oh, yeah, good point. So this is half, and then so we just multiply it by 2. Okay. All right, let's see the homework set and see if we can do one of these problems here. Length of the curve to 4 decimal places. Let's do this one as another example. This is similar. Let's see. Is it an arc length? That one has theta's given. All right, let's do this one. Let's do the one that's similar to the one we did, just so we can check it in our calculators. Well, it is different because cosine 2 theta, we don't know how this is going to be drawn. And so I use a calculator to find the length of the curve, correct the 4 decimal places. Length of the one loop of this thing. So this thing is apparently looping, and so we want one loop of this. We could try to imagine how this thing might look like without the graphing calculator first. And this is cosine theta that is going to have a period of pi instead of 2 pi, so it's going to be squished. So it's going to finish its looping there, and this has r is equal to 1, amplitude of 1. So let's imagine how this thing might look like. It starts off when theta is equal to 0, 1. Where does it cross the x-axis? When does it go back? Pi over 4. So pi over 4. And then what happens, and I don't know if you guys, we talked about negative, right? When the thing goes negative, and I think I had this little arrow thing going on here. At pi over 4, it's pointing this way, and it's 0 right here. And then if we continue to take that and turn it, it's going to go negative. And then when is it going to hit the axis again? Where? 3 pi over 4. And then this low point over here, where's the low point? Pi over 2. So at pi over 2, I'll be farthest away. So at pi over 2, it looks like I'll be here. I'll be in the negative direction. I guess I was drawing this in blue. And then if I continue to turn this at 3 pi over 4, which is right here, then I'm going to be back at 0. So it looks like the same loop as we had, doesn't it? No, it's a little bit different. Oh, no, it's going to be a lot different. It's not the same loop as we had. So we're here at 3 pi over 4. We're back at 0. And then we go all the way to pi. We turn this to pi. And then our graph was at 0. And then it goes positive again. So it goes positive and it goes down to here. So by the time you're at pi, you're going to be the farthest in the positive direction, 1 unit in the positive direction. So can we see the graph, the rest of the graph? Can you picture the rest of the graph? It'll have 4 petals, right? All right. So I'll just draw the rest of the petals. And then now let's decide on how we want to integrate this and which way, what our limits are going to be. So it looks like we're going to have a lot of options. Any suggestions on how we want to do these limits? 0 to pi over 4 would get you half of 1 loop, and then you double that and you get the whole loop. So that's probably the easiest. It's positive. We're taking advantage of symmetry, so that's probably the easiest to go. So theta is equal to 0 or pi over 4. And then we'll look for this arc length and then just double that to get the whole loop. So we have our R, which is f. We would call f of theta, cosine 2 theta. We need the derivative, which is negative 2 sine 2 theta. And then we punch it into the formula. We're going to double it. And then the integral is going to be from 0 to pi over 4 and the square root of 2 sine 2 theta squared plus cosine 2 theta squared d theta. Let's figure it out. Yeah? So we're integrating square root of 2 sine 2 theta squared plus cosine 2 theta squared, close the square root, when we go from 0 to pi over 4. What's E? So it looks like we have an elliptic integral involved here. That fortunately we don't have to worry about. So 1.21106. This is oh, well, I can double 1.01. Wait, 1.211. 4 decimal places. 2.22. What? 2.4221. All right, let's see. All right, good. So that works out. Let's just remember to remind ourselves to double this, and to double this. All right, questions? Okay, I think that's about all that's involved in the calculus. So what do you think the difficult parts about these problems are? It's not the integral, because I'm not going to expect you to calculate these integrals. What? Finding theta. Okay, that's probably one of the most difficult parts in these types of problems, is finding theta. So in your homework assignments, they're going to be asking you where some of the things intersect. So any strategies for finding theta? What? Graph it. Okay, you guys have tools to graph things. So use your tools to graph things, graph it, and then find an intersection. Now, I tried to graph this without using tools, right? Because you should be able to, but I think that is not that it's a waste of time, but I think that could be time consuming when you do it that way. But I think you should try to do this by hand once in a while without graphing it, and then eventually try to graph it and see how it goes, see if you got it correct or not. So when you're first doing these things, you know, when you have a function like this, try to see how it would look like in Cartesian coordinates and then transfer it to polar coordinates and see how it might look like. And then part of this also is just practicing doing a bunch of graphs in polar coordinates. And if you look at one of those websites and look for like a online graphing calculator in polar coordinates, usually they have a variety of examples and how things might look like. So you can see how a cardioid would look like, and you can see how one of these loops would look like. And then after a while, you get to know certain properties about them, and that if you have a cosine of something times an angle, if that something is odd, then you'll have that many loops. If that something is even, then you're going to have twice as many loops. So you get to see these little gems pop up that instead of just having somebody tell you about it, well, if you discovered it yourself, it's kind of cool. Well, that's for this one. Now try sine. How's sine going to look like? The sine's an odd function, so you'll have weirder things. Yeah?
I can figure out if Windows
if you have no idea what's going to look like, to see, at least you should know how it looks like in Cartesian coordinates. And from there, you know, with an angle of 0, an angle of pi over 2, nice easy angles like that, try to figure out what r is. If r is 17, and then you take out your graphing calculator, and your graphing calculator looks like this, then, you know, oh, r is 17, so I must need to go 17 units this way to see a little bit of the function. So that's how you can start. And when theta is equal to 0, what is r? And that's going to be in your positive x-axis. And then when theta is equal to pi over 2, what is r? That's going to be in your positive y-axis. And then you look for it there until, what is that? The theta min and max, it's always usually safe to go from 0 to 2 pi. And then sometimes 0 to 2 pi might draw things twice. Like another family of curves would be just like, or even, 17 times sine theta from 0 to 2 pi. When you first see this graph, you say, oh, okay, so this is the thing that's being drawn from 0 to 2 pi. But if I don't go from 0 to 2 pi, what if I just go from 0 to pi? I see the same picture. So this actually, this graph is going to be drawing that circle twice if you go from 0 to 2 pi. So if I go from 0 to pi over 2, I only get half of that circle. So that's another good point, is to try to figure out your window, try to see what r values are for 0 and for pi, or pi over 2. And then once you do that, you get some idea of how your pi limits would look like. And then try your theta going from 0 to pi, try your theta go from 0 to pi over 2, and see how they compare. And then this is again, sitting down with a graphing calculator, punching all these different parameters, values, and see what you get. And then it's just practice. Yeah?
So something I struggled with yesterday on the was the final problem, which we were asked to draw a graph based on the our values we were given. It took me forever to figure out how to do that. Is there like easy zoom to that was like?
In your handheld graphing calculator, if you look for zoom fit, that'll generally give you a view of most of what you're looking for, and then you can adjust it from there. All right. So we're all good here, yeah? 10-4 under our belts. Yes. No, this 10-4 is being covered today. Right? In our schedule? Yeah, it's still doing. I'm not going to change that. So I don't think I would make a due date sooner than what it was on the thing. So I'm not gonna move that. But it is it's what we're supposed to cover today. All right. Any other questions? Okay, let's go on to the next section. Okay. 10.3, number 2. Let's see. What's 10.3? Polar coordinates?
Yeah.
Yeah. Number 2. So this will give you a good idea of how polar coordinates kind of work out and how they end up repeating, and how one polar coordinate point might represent, or one Cartesian coordinate point might be represented by multiple polar coordinate points and stuff. We're doing B. Is that what we're doing?
A was really straightforward, and then B, you had the first one, you had to throw that 2 pi in there.
Okay. All right, find the polar coordinates r theta of the point where r is bigger than 0 and r is between 0 and pi over 2, or 2 pi. So we need 2 comma negative 5. Oh, we're down below. 2 comma negative 5. And so we want r and theta, and I think r is just going to be the distance from the origin to that point. So r is going to be the square root of 2 squared plus minus 5 squared, which is 29, root 29. And then now they want theta. They want theta between 0 and 2 pi, so it would be nice to figure out what this angle is, but you have to find out this angle over here. This is the angle that you want, so we don't want this angle. We want this angle that goes around. And we have the relationship for theta in x and y, right? And that's a tangent. So tangent of y over x is equal to theta. So theta is equal to the tangent of y is negative 5 over 2. Yeah. So yeah, if you just put arctan theta only gives you values between negative pi over 2 and pi over 2. Did you know that? Trig? Yeah. So it's one of those things I kind of stress in my trig classes. I haven't taught trig in like 7 years. Anyways. So if you just do the arctangent, it's only going to give you values between negative pi over 2 and pi over 2, which is going to be this red mark that I just put here, right? So what we want to do is you can continue to find the arctangent and then just make it go around one more time by adding 2 pi to it. Does that make sense? So
Same thing, but it's just
oh, sorry. This is arctan. So what we want to do is this theta right now is between, not including, negative pi over 2 to pi over 2. And if it was positive, then you'd be good because it would be between 0 to 2 pi. It would be positive. But this will end up being negative because, you know, tangent is negative and all students take calculus. Tangent is negative in this quadrant. So you have to add 2 pi to that. So the new theta, let's call it theta prime, is going to be the old theta plus 2 pi, which is a negative whatever that angle is, plus 2 pi, and then that'll give you that limit.
How about the last part there, less than R is less than 0?
So r is less than 0. What kind of values do they want here? They want decimals or?
No, they want the root 29
And then the actual arctan
plus
written out?
pi.
Okay. All right, so for this one, if they want it pointing the other way, so we're still looking at the same graph right here. So if we're pointing in this direction, then remember that the whole idea about that pointer, pointing in a positive direction and pointing in a negative direction? What you could do is, let's see, we do a green graph. So you can point in this direction where this is -2, positive 5, right? That's across the origin from this original point that we're looking for, which is 2, -5. If you have your pointer pointing in the other direction, then and have your r go negative, then it would be pointing to the same point. You'll end up on the same point. Does that make sense? So if I have my pointer pointing in this direction, I can designate a negative r. So that's my r, negative. But then I have to have my angle pointing this way. So based on this angle over here, theta, which is the arctan of -5/2, that's this red angle over here. This is theta. What is the new theta? Let's call this theta double prime. What is this theta double prime that I want? It'll be this theta, the old theta, plus pi. So we'll take arctan of -5/2 and we'll add pi to it, and then we'll be pointing in that direction where we send our r backwards. Would it help if I had arrows? That's my theta pointing in the direction that I want, and that gives me a positive r. This is my theta pointing in the opposite direction from what I want, and that would be a negative. One person understand that. Well, Brian's the one that asked for it, right? Anybody else think this is okay, or this is just, whoa, jacked up? What are we doing? So this is all about that trig that we were talking about at the very first day of class. That's the requirement. So all right, well, look at these notes and think about it and see how you could approach this problem. Having negative r's, I tried to stress those negative r's when people were doing stuff on the board and having them go negative. And that's just your pointer pointing in a specific angle direction, but then your r is going backwards. It's going behind you. And that's how some of the polar coordinates are drawn. And so we have to be able to deal with that. All right, I guess we don't get to start the new section. See you guys on Monday. Good luck with the homework. Homework's due on Sunday up to 10:03.